Okay, the plan for the day is to finish chapter 12 and do the remainder of the homework problems. I'm pretty sure we're on page around 413. And yeah, oh no, we're not. Let's move back. Yeah.
It was like 372 or 373, no? Or 376, I think. 376, 13 or 12.4, wasn't it?
Yeah.
Yeah, 376.
We started 4.5.
Yeah, we started 4.5. So we're on 378. Yeah, 378.
Yep. I will agree with that one. You would agree with anything.
I can imagine.
Section 12.5.
I can concur. That's right.
Related?
Okay, a capacitor has a quality factor Q, and we're going to take
Oh yeah, you gotta dig around.
the resistance that's part of the capacitor divided by the X of C. So the capacitor is going to have some resistance associated with it, and DC resistance. So the DC resistance through something that's open is going to be very big. And so that's going to be on the order of megohms. And I'm going to divide that by the number of ohms that I have. So Q is going to be a pretty large number. In any capacitor, we have two components. We have a capacitive component and a resistive component. And normally we ignore the resistive component because it's so small. Well, I guess that covers just about everything. Oh, look at this. We have codes, value codes.
We're done.
Yeah, we're done. So on page 382 on the bottom, you could have a B, C, D, E, F, G, H, I, J, K, L, and those are you could have tolerances of your thing, but clearly that's not. Okay, well we're done with all that. So now it's time to go back and work homework problems. Anybody know where we were?
19 was when we stopped on.
Yes.
Didn't do it.
So I gotta do 20.
Yeah, we did. We did 19.
It was oh yeah, we did. The answer is no.
Okay, so I'm doing 19. No, I'm not doing 19. I'm doing 21, 31, and then 13 one.
Why is 9 the last one I did? Oh, yeah, 19 no. What? And 24 you could.
Okay. 24. I have to turn the page.
Privilege.
The source in the picture above has a frequency range. No, yeah. Calculate the range of Q. All right, so I got to find the range of Q. And it's the B guy. Okay, so my frequency is going to go from 60 hertz to 3K. So that's the range of my frequency. My X sub C is 1 over 2 pi FC. So 1 over 2 pi 60 hertz times capacitance 0.22 microfarad is going to give me some number. So I'll figure out what that number is. 2 times pi times 60 times 0.22 minus equals 1 over K. We'll call it 12K. 12K ohms. And then we'll do it again. X of C 1 over 2 pi 3k 0.22 micro. Right. 2 times pi times 3,000 times 0.22 minus equals 1 over key 241. We'll call it 240. 240 ohms. Then we know that Q is going to equal RD divided by XL. So Q at 60 hertz is going to be, and they tell us RD is 200 megohms divided by 12k ohms. 200 EE6 divided by 12 EE3 equals we'll call it 17,000. It's going to be unitless, so there'll be no units there. Q at 3 kilohertz, 200 megohms divided by 240 ohms. It's in the problem. So 24, the last, just before the period, at the end of the last sentence. I know you wouldn't normally get that far in a problem. You know, reading it through, you normally get about a third of the way through, and so you might. But I have to know it, because without knowing it, I can't work the problem. So I don't have a choice there. 200 EE6 divided by 240, and it looks like we'll call it 830,000. Keeping that I only have 2 significant digits. Again, Q is going to be something that has no units associated with it. So the range, always range of Q, anywhere from 17,000 to 830,000. All right. Well, was that easy enough? Not really. Not unless I just went over it before I got to the problem. Then I would have been wondering how. But I just went over it, so it wasn't a problem. 31. 31. The relative permeability of material is the ratio of the permeability to that of the free space. The relative permeabilities ratings for several common dielectrics are shown. Okay, I got it. Determine which of these dielectrics is used in
permittivity or permeability?
Permeability. What did I say?
Permeability. It's permittivity.
Oh, I'm sorry. Permittivity?
Is there a difference?
No.
Okay.
Yeah, how you pronounce it. All right, permittivity. Yeah, the other word probably doesn't exist in the English language. But other than that, determine which dielectric is used. Okay, so I have this thing and it says the capacitance is 0.022 microfarads. I also know that the capacitance is, and of course I forgot that equation already, so I have to go back and find it, because that was 2 days ago. You wouldn't expect me to remember it since then, would you? Okay, so it'd be epsilon naught, epsilon r, A over D. A over D. That doesn't look like a D, does it? That doesn't look like much of a D. Okay, so that's what we have. We also know from our picture that area is 5 times 10 to the minus 2 meters squared. And we also know that we have to be in meters, and that my distance between the plates is 1 times 10 to the minus 4 meters. Okay, so we're going to write this and say, and we're going to put everything into this equation. Okay, changing color to blue. 0.022 microfarads is equal to 8.85 times 10 to the minus 12 times epsilon r times 5 times 10 to the minus 2 divided by 1 times 10 to the minus 4. Now we're going to use our 9th grade algebra skills and write that epsilon r is 0.022 microfarads divided by 8.85 10 to the minus 12. Oh, and I was doing so well too. Minus 12 divided by, okay, this is minus 4. It goes up there. That makes it a plus 2, so it'd be 500. All right. So now it's time to break out the calculator. 0.022 EE6 minus divided by 8.85 EE12 minus divided by 500.
Divided or multiply?
Divided.
Oh,
Yeah. See, it's underneath that divide line.
nobody, I thought you were solving it.
No, we're trying to solve for epsilon r. So that guy dividing. Oh, I had to get up out of my chair. I don't believe it. Last time that's going to happen. Hey, what's the button here? I didn't push the right button yet. Oh, let's see. Third function changed to scientific notation. 9.9 times 10 to the minus 3. 9.9 times 10 to the minus 3. And epsilon r is also something that doesn't have any units associated with it. So now we look over here and see relative permeability 1, 7.5, 5, 2, and 6, and we have something times 10 to the minus 3. What does that mean? That means we don't have the right answer. That's what it means. All right, so that means I have to put it in my calculator again. You got 1.2? 0.022 EE6 minus divided by 8.85 EE12 minus divided by 500 equals 4.97. We'll call it 5. All right. Eraser. I think because I got out of my chair, I hit the equal key twice or something. 5.0. All right, so now we're going to write down the final answer. Oh, it's mica. M-I-C-A. Now, is mica a element or is mica a mineral?
Mineral.
Right, so it's a mineral, right. And it's used in a whole lot of capacitors. It's a normal thing for capacitors to be using mica. Okay, moving on to section 13.1, because the syllabus says we have to do 13.1 today too. Okay, so we're going to have our chapter 13, section 1. And we're going to have RC circuits, which means I'm going to have a resistor and I'm going to have a capacitor. Or I'm going to have a resistor and a capacitor. Or I'm going to have a capacitor and a resistor. Or I could have a capacitor and a resistor. I could have any of those things. Except 13.1 only has to do with the series guys, so we only have to worry about them. All right. If I have, all right, so I'm in series. Is that right? Okay, so I have I before E, except that, okay, so that must be right. And I have two resistors, resistor 1, resistor 2. So resistance total, I'd better be, I add both of them, right?
Yep. And this one.
All right. And I have two inductors, L2, L1, and I'm going to get inductance total is going to be L1 plus L2. Is that correct? Is that correct?
I think that's going to
Is that totally correct?
That'll be 1 over.
Huh? That's not totally correct. That's correct. But it's not totally correct because it's plus or minus the mutual inductance that might be associated with those two guys, right? Remember the mutual inductance? So if I don't give you what the mutual inductance is, or give you some way to calculate it, then you have to, then your L1 plus L2 would be correct. But if I tell you it has some mutual inductance, then you'd have to either add it or subtract it, depending on which one would be wrong. Whichever one you choose would be wrong. I'd mark it the other way, right? And then I have two capacitors. So totally correct, plus or minus mutual inductance, correct, add L1 and L2. I got C1 and C2, and my total capacitance is going to be 1 over C1 plus 1 over C2. Okay, so I'm going to do it again. I've got two resistors, R1 and R2, and the total resistance is R1 plus R2. And I have two inductors, XL1 and XL2, and I want to find the total reactive inductance. Is that called acceptance? I forget. And that's going to be XL1 plus XL2. And I have two capacitors, and I know XC1 and XC2, and I want to find XC total. That's a total. What is XC total? Huh? Did I say anything? Wake me up when somebody has an answer out there. Yes.
Isn't it what you just did over there, 1 over?
Yeah, that's what I was waiting for somebody to give me the wrong answer. That's yeah. So it's XC1 plus XC2. Now, why is that? Why, when I took the capacitance, I had to use this 1 over rule, but when I was using capacitive reactance, I'm just adding them, other than to confuse the student. Why would that be?
Good job.
Did I confuse you already?
Oh, you bet.
Excellent. Well, if you remember, x of L is 2 pi FL, and x of C is 1 over 2 pi FC. So when I calculate the x of C value, I'm already throwing in the 1 over thing. Okay, so when I change it to x of C, I'm in ohms. So I treat the x of C value just as I treat ohms that are real, from a resistor. I'm going to have an imaginary number and go negative on me. That's a different issue. But when I do the calculation, I can just add them and be there. So that means if I'm given, I could ask what the total capacitance is given X sub C1 and X sub C2. I could then calculate it and then say the total capacitance would be 1 over 2 pi f X sub C total. See, so now I'm doing this, to get the total capacitance, I'm doing the same thing. I got 1 over 1 over 1 over saying it right. Yeah. Okay, well I sure am glad I got you on that one. Okay, so I got some source resistance, I got some source voltage, I got some voltage across the resistor, voltage across the capacitor, and I got some voltage across the source. Voltage across the source squared is the voltage across the resistor squared plus the voltage across the capacitor squared. The voltage across the capacitor is 90 degrees out of phase with the voltage across the capacitor, resistor capacitor, so I'm using Pythagorean theorem. That's what it is. I remember Pythagorean theorem. Voltage source equals square root of voltage across the resistor squared plus voltage across the capacitor squared. RMS voltage, RMS voltage, RMS voltage, peak voltage, peak voltage, peak voltage. I can do it either way, but I need to make sure I don't switch apples and oranges in the middle of the calculation. I'm going to have some phase angle associated with it, and going to be the arctangent, and this is pretty silly, minus the voltage across the capacitor divided by the voltage across the source. And when I do that, that's going to give me a negative phase angle. So I look at an XY coordinate thingy, and I'm going to be down that way. My phase angle is going to be sitting right there. X of V. V, voltage across the capacitor, voltage across the resistor. Okay. Series impedance. So I have the same guy in series. I want to find the impedance. That's going to be the square root of R squared plus X sub C squared. I have to find the capacitive reactance to get it. If I want to find the phase angle of the impedance, I have to take the arctangent of minus X sub C divided by R. Now, the reason I'm putting the minus sign there is because X of C is a positive number. 1 over 2 pi f C is going to be a positive number, but X of C is sitting on the imaginary negative part of the imaginary axis. So I'm giving it a negative number instead of saying X of C angle minus 90. I'm giving it a minus angle so that I can get the phase angle right. Give it a minus magnitude so I get the phase angle right. Well, I guess that's all there is. Let's see what homework problem we can do for the first part of chapter 13. Oh, look at this. After we're done with chapter 13, we do a test. Isn't that lovely? So next class period, which is the 13th. Yeah, I don't think anything's happening on the 13th other than this. We have to do the rest of chapter 13 and a review so we can do a test on the 15th. Oh, isn't that great? Just before the holiday? I think so. I think that's marked number 1. There is no number 1. Oh, yeah, I found it. Number 1.
417?
Yeah, I found it. The component voltages are shown below. Determine the magnitude and the phase angle of voltage source. Okay, so I've got a capacitor, a resistor. I have 12 volts. I have 4 volts. And I got some source guy sitting here. Boy, that was really bad. Oh, that's better. So voltage source is equal to square root of 12 squared plus 4 squared. So that's 144. That's the square root of 160, right? 160, which is oh, it's not even 13. Yeah, 12.6. 12.6 volts. We want the phase angle. It's going to be the arctangent of the capacitive guy on top minus 12 divided by 4. That looks like a 3, doesn't it? Okay, so 3 with a minus sign, second function, arctangent, minus 71.56, we'll call it minus 72 degrees, minus 72 degrees. All right, well, that was marvelous. Yeah, number 6. Number 6. Got to turn the page. Calculate the impedance, the total current, the voltage across the capacitor, the voltage across the resistor, and the phase angle for the circuit shown in B above. All right, so I got a circuit in B, 12 volts, 1.5 K. And well, that's my capacitor. So I got a capacitor there, I got a resistor here.
1.5 hertz, right?
0.0, oh yeah. Doesn't it look like a hertz to you? Is that better?
Thank you.
2 microfarads and 120 ohms. Okay, so that's what I got. And what else?
22 is supposed to be 12.22.
Oh, I put an extra 0 in? Either put an extra 0 in or I don't know what I did. Is that better?
Thank you.
All right. So we want to find total impedance. We want to find total current. We want to find the voltage across the capacitor, the voltage across the resistor, and the phase angle. Okay, so those are the things we're doing. All right, so first thing we're going to have to do is figure out what x sub c is. 1 over 2 pi. Is it 1.5? Yeah. 1.5 kilohertz times 0.22 microfarads. So that's the first thing we'll calculate. 2 times pi times 1.5 times 0.22 minus equals 1 over k. Looks like 480 ohms. 480 That was good. That was just so great. 480 ohms, angle minus 90, just in case. And we already know that one. Okay, so total impedance, square root of 480 squared plus 120 squared equals. Looks like 495. Can't tell in this light, but that's about what it looks like. 495 ohms. So 495 ohms.
Ohms or degrees?
Ohms? Why are you complaining? What is the problem in the front row anyway? Can't listen to me. All right, so we're going to find this guy at arctangent of the minus XC guy, 495 divided by 120. Minus something. 495 divided by 120 equals, with a negative sign, arctangent. Minus 76 degrees. Minus 76 degrees. Is that better? All right, total current. Okay, so total current, voltage divided by impedance. Anybody remember the voltage? 12 volts. 12 volts divided by 495 ohms. 12 divided by 495 ohm, 24 milliamps. 24 milliamps. All right, voltage across the capacitor. 480 ohms times 24 milliamps. 11.6. 11.6. 120 ohms times 24 milliamps. You know, I bet you that's probably 12, isn't it? Why don't we use the numbers that are there? 480 times 0.025. No, it's not. All right. We're gonna come across this guy different. We're not gonna do that. We're gonna take the square root of the source voltage, 12 squared minus 11.6 squared. And so 12 squared minus 11.6 squared equals square root. We'll call it 3 volts. Call it 3.1. 3.1 volts. Now if we would have gone 120, 120 times 0.024, we would have gotten the same 3 volts, so it doesn't really matter. When I get done rounding it off. Am I done?
Yep.
Did I get that one right? Anybody look in the back of the book to see if I got it right? 19. You actually bought a book? Oh, we can't do 19 yet. We haven't gone that far. So that means we'll have to go home.
Shoot. You didn't see your presentation? No, I was so. We would have went to